thanks a lot to Michael and Rasmus for inviting me. This is a different kind of talk than the talks you've probably been hearing over the summer school. There is a hashing component to it, but it's hidden, and also it's more of a bad news talk than a good news talk. I'm not telling you how to do hashing, I'm telling you what situations where hashing is not going to help you. In other words, I'm going to talk about lower bounds. So, as such, this is by the way joint work with my student, Amir Ali Abdullah, we're both at the University of Utah. And there are a number of different concepts that are going to swirl around the stuff I'm talking about, and it took me a long time to understand them, if I can claim to have understood them myself, so I'm not expecting that you will, I don't think I can actually explain all of them in great detail at this talk, but I'll hope to give you some kind of high-level idea of how these different ideas fit together, and what part of them might be useful in your ongoing work. So the story involves a number of different things. One part of the story are these things called Bregman divergences. These are distance-like functions that are very popular and well-studied in machine learning. I'll say a little bit about them. They're important for various reasons, and they also have a very nice connection to geometry, because in some ways they generalize standard point-line duality, projective duality that we use in computational geometry in a very interesting way. So that's one element of what I'll be talking about. What I'm talking about is doing near-neighbor search with these divergences. Again, this is interesting because near-neighbor search in particular is a very interesting problem, and these distance functions come up in a lot of problems, especially in image analysis and in speech analysis and in audio. And so we want to look at near-neighbor search. We're looking at approximate near-neighbor search. But what I'll be talking about today, in fact, we have some prior work on how to do near-neighbor search, and we want to see how far we could push the work, and then we hit a roadblock. And the roadblock will be what I'll talk about, which is basically lower bounds. In particular, we're talking about lower bounds for hashing-like structures. Our basic idea was, well, we have this weird geometry, and we want to do near-neighbor search with it. We know that locality-sensitive hashing is this awesome tool to build a data structure for doing near-neighbor search. Can we do LSH-type things for these strange distance functions? And this paper is basically one way of saying probably not. And that's what I'm going to be talking about in this self-built part. And I'll explain all of what all these things are, so you don't have to know any of them right now. But really central to all of this, even though this is what the talk is about, what's really going on underneath is something which is far deeper, and a lot of people have worked on for many, many years. Is this idea of these what I call isometric inequalities in the hypercube. It's a way of saying basically that any interesting function you define on the Boolean hypercube has high expansion. It expands out in strange ways. And because of that tool of expansion allows you to prove lower bounds on many problems. It's a very powerful tool. In one form, it goes back to the late 80s, but it's been used, especially in the last 10 years, if you look at the work of Ryan O'Donnell and others, has been used very successfully for all kinds of problems. And we're going to be using a generalization of that we introduce here, which might be interesting. And that, of course, connects to things that you may be more familiar with, things like calculated hashing, and also this partial match problem, which is like the core hard problem in this area of the world that we live in. So that's sort of the overall large sort of the global map of the things that I'll be referring to. And now I'll try to drill down into some of these more specific things and explain what we're doing. And feel free to interrupt at any point with questions or anything you have. Because I'll be giving a high-level view, but I'm happy to drill down for anyone who has more specific questions. So let's start with Bregman divergences. They're defined in a kind of a natural way, but and then we'll see exactly why they're defined this way. So they're parameterized. So the idea is you give me a convex function phi, and I'll give you a distance function, parameterized by phi, and in this following manner. So given any convex function phi, you define the d phi p comma q as this weird function up there. Geometrically speaking, what's happening is that to estimate the distance from p to q, and this is directed, so distance from q to p is different, you look at what would happen if you approximated the convex function phi by its first order approximation at q, which would be basically the second two terms in that expression. It'll be phi of q plus the gradient term, and that'll be that line there. Of course, that's a first order approximation, that's a convex function, so it's always going to be below the true value. So there's going to be some difference, and that difference is your distance. It's a very weird way to define distance. Okay. But think of it as a measure of like a second order term, essentially, how convex this function will be. So this function were linear, for example, this distance would always be 0. Yeah. So why is this interesting? It's interesting because by plugging in different values of the convex function phi, you get different functions that we actually recognize, and that we wouldn't have known are part of the same family if we didn't have this common gradient. In particular, the squared Euclidean distance is a member of this family. You plug in phi of x equal to x squared, you get this one. You can recalculate. More interestingly, a very core measure in information theory called the relative entropy, or the Kullback-Lever divergence named after the two people who first developed it. Again, it's a member of this family. And again, just mentioning three of the more well-known ones, but there are other ones you can plug in for any context. And that's the point. The point is that they're all related by the way they're constructed. And that means they share certain properties. They share some other properties as well. Some other actually very nice properties from a statistical point of view. In particular, so before we read the slide, let's just imagine we're talking about a Gaussian distribution. We know that a Gaussian distribution can be written as law, can be written as e to the minus the value x minus the mean squared divided by some clear variance. Let's say it's a very simple one-dimensional Gaussian. So what you're saying is that if you look at the mean and you look around it, the density falls off exponentially, controlled by the squared Euclidean distance of that point you're looking at from the mean. Okay? So Gaussian, exponential fall off, squared Euclidean distance. Suppose I didn't have a Gaussian. Suppose I had a different kind of function that was part of this general family of what I call exponential distributions. Not the exponential distribution, but a general class of distribution, like the multinomial or something. It turns out they have the same fall off, but the fall off is no longer measured with respect to squared Euclidean distance. It's measured with respect to something else. It turns out for every such distribution that something else is an associated Bregman divergence. So in some sense, the Bregman divergence capture the natural notion of distance in terms of fall off and probability. Right? For a Gaussian, the natural fall off is squared Euclidean, which is why Gaussians and Euclidean distance seem to go together so well. Right? Whenever you think of one, you tend to think of the other. But for a multinomial, it's a KL divergence, and so on and so forth. So these divergences are not just a generalization of Euclidean distance in the geometric sense, they're also a generalization in terms of modeling distributions. In some sense, if you're dealing with a certain family of distributions, this is the right distance to look at. If you and I would take these statements with a grain of salt, but there is some sense which is natural. And so that's why it turns out in machine learning now, when people have developed different algorithms for different kinds of class of distributions, they looked at them and wondered, oh, wait a second, these are really doing the same thing. And I realize this because I now know that these are the same Bregman. They're just part of the Bregman family. I can define a new algorithm that just works for a generic Bregman divergence, and it captures all these properties. So things like, say, k-means or the EM algorithm for clustering, they work for a Gaussian distribution, but they work for, in fact, for any Bregman divergence. So if I'm doing a mixture estimation for a class of multinomials, the same algorithm will work with a different geometry. So changing the geometry allows you to deal with different kinds of spaces. And that's what's nice. Oops. It's a sign I should talk less. Bregman divergences from a geometry point of view are kind of low. And especially for dealing with high-dimensional geometry problems, they're particularly low. And the reason is that, well, first of all, they don't have triangle form. You can have things like the above. You can have a distance from P to Q, that's 0.01. Distance from Q to R, that's 0.01. But the distance from P to R is 100. And these numbers are artificial. I can make them as big as I want. They're just very, very bad. And they also don't refer to symmetry. You can have a distance from P to Q that's 1, distance from Q to P that's 100. And again, if you in particular look at the Kullback-Leibler divergence, this kind of makes sense information theoretically. But it just makes life difficult. And of course you can say, well, what about the square Euclidean distance? That's the only one that actually is symmetric and it doesn't satisfy triangle equality. The square Euclidean doesn't do it, but at least it's symmetric. So if you want to design algorithms for these problems, as opposed to just doing statistical inference to them, you face a big problem. We don't have the tools that we rely on for doing all kinds of geometry, especially approximate. The reason I harp on the approximate issue is because whenever you're doing things approximately, you're saying, okay, I have to measure these distances. I can't measure them exactly. I'm going to measure them approximately. Maybe I'm going to sample some points in my space. Maybe I'm going to do shortcuts. The minute you do that, you're relying on the triangle equality to help you say that, look, my shortcut is not going to cost me. And you can't do that anymore. notion that you can write this as a second order expression. After all, it's a different function, it's first order approximation. It has to be some kind of second order term. Right, and of course, it's a second order term in a vector space. You're dealing with things like a Hessian of V. And remember, since this is convex, this will be positive. Which means that if you go to the limit when the 2 points become arbitrarily close, the distance from P to Q starts looking like this, which is a very well-known distance in sort of data analysis. It's called the Mahalan distance. It's basically a skewed Euclidean distance. You take, instead of all distances and all axes being the same value and all axes being orthogonal, you're transforming it by linear transformation, a non-singular linear transformation, and you're measuring it. So your ball becomes an ellipsis. So in infinitesimally, these Bregman divergences all look like a Mahalan distance. And if that were the case, that would be very easy, because you can easily transform a fixed linear transformation space just by a standard diagonalization, and you can just get another Euclidean distance. It's very easy to construct such an embedding. So a space with a skewed Euclidean distance is the same as a space with Euclidean distance from the point of algorithm design. You just insert an appropriate linear transform. The problem, of course, is that this changes as you go across the domain. So in some places you look almost okay, in some places you look very skewed one way, some places you look skewed another way, and that's where the complexity of these divergences come from. And it's a non-uniform. It's almost, one of the thinking was like, it's like having a Riemannian manifold with variable curvature. At every point, for any fixed point, the curvature gives you a fixed locally Euclidean space, but now it changes. That's what it is. And so you can quantify this notion of asymmetry in many ways. What we'd like to do is say, okay, we have an algorithm, we want to take our algorithm and run it on these strange distance functions, and our running time will depend on normal parameters like n and d and epsilon, but it'll also depend on some structure constant of the distance function. And we'd like to produce such a number that we can get a handle on and say, okay, look, if this number is small, we are well behaved. If this number is 1, we reduce to the standard case, and if it's large, we don't know what's going to happen. And so you can define, and in previous works, people have studied these things, and you can define this in 8 different ways. They're all more or less equivalent. And I say more or less in the sense that if the overall curvature of your space is bounded, they're all bounded. And if the asymmetry, that simple expression, the ratio of going one way to the other is unbounded, then they're all unbounded. But they're not equivalent to each other. They can vary amongst each other. But for purposes of discussion, they're more or less the same. And if you focus on just the first one, the going round trip, going coming ratio, that's the number we want to think about as a measure of the badness of this distance. Yes. So like I said, there's been a lot of work on this topic, mostly in the realm of clustering and also in the realm of nearest neighbor search. And again, there's been a lot of heuristic work because people in the sort of more applied areas, especially in computer vision, want to use these distance functions, in particular because they come from histograms. One way of comparing histograms is as think of them as a distribution, normalized, and then use something like relative entropy or the chi-square distance or the other or Jensen-Shannon or things like that. And so people are studying this in practice, and there's been theory work as well. And they all involve this structure parameter mu in some form, this measure of asymmetry in different ways. And they all, you can either assume nothing about mu and get weak bound, you can assume that mu is bounded and get better bounds, and there's all flavors of this. And so the question that we're trying to answer, that we tried to answer in this paper was, is this structure concept intrinsic to the study of these divergences? Are we just not being smart enough? Could we get rid of this and just get out and look exactly Euclidean? Or is there something fundamental about this variable curvature that's going to make life very difficult? And that essentially is, the answer is kind of yes. And the particular vehicle we will choose to give this kind of yes answer is the approximate near-neighbor problem, which again is a very well-known problem. You're given a bunch of data, you're given n points in d dimensions, and you want to process, I said 1 plus epsilon, let's just pretend you want constant approximate nearest neighbor. What does that mean? Well, I have a query Q, this is the exact near neighbor. I don't want to give you the exact neighbor because it's too much work. But I'll give you an approximate near neighbor that's kind of close. And the kind of close is measured by a multiplicative factor. It's a standard equation. And the reason is that the exact nearest neighbor is very hard to do in dimensions. This is just a natural. And what you want is sort of reasonable query time and reasonable space. Right? You want to build a data structure that, every structure should look like, data structure should look like binary search. Log n query time and a linear space. Or even build a log n if you're using integers and things like that. But we can't always get that, so we want log n query time and kind of near linear space, if we can use it. And we also want polynomial dependence on t and the error terms, because otherwise we're both. When you have 16 million dimensions for your 3 grams, then you really don't want, you don't even want t squared, but that's another story. You want something small. So that's the problem we'll be looking at as a way to understand, can we do anything in high dimensions? I should mention, by the way, that to show lower bound, so I must give you a model, and we're working on a model that's reasonably well studied in this data structure world. It's called a self-probe model. And the idea is that I build a data structure, and I'm going to make queries to the structure. So I'm going to express my bounds in terms of how many lookups I need to make in the structure. I don't care about what other computation I do. It's a lower bound, so my actual write time is going to be worse, but that's what I'm doing. Okay, and this is being used very successfully for all kinds of lower bounds, for things like locality-sensitive hashing and other related data structures. So this is a very natural model. So in particular, you'll have m rows, and each row has w entries in it. I'm going to make r probes to solve my query. So my query comes in, I'm going to make r probes into the structure, and I'm going to develop an answer based on that. In this paper, we work in what is called a non-adaptive setting, which is a weaker setting. It assumes that you make your r probes in parallel, in some sense, and get the answer. You're not allowed to make a probe like, oh, that's the answer, and go and change your probe for the next one. Okay, that's a weakness in some way. We were hoping to sort of make that implement. It's easier to think about that. Any questions so far? No.
I didn't understand the last part you said. So
The non-adaptive thing?
So if the answer is yes, I cannot say, well, the next time I'll query smarter.
Sorry, I didn't
You're
understand.
saying that the adversary cannot use the information by one query to change the next query, or
The
It's an
algorithm.
algorithm that can't.
The algorithm, so it's a model that makes the algorithm work harder.
So it's a little bit like Bloom filters. In Bloom filters, you decide in advance exactly where you want to go, but if you have two-level hashing, in the first level you go somewhere, but that gives you a new hash function to use for the next
Yeah.
level. So
That's
he's
right.
only proving lower bounds for the case where you only use the query to decide
That's
which parts of memory you ask.
okay. So
Just like in Bloom filters.
right. So this is a lower bound for certain kinds of algorithms.
Yes.
Not a general lower bound.
No. That's the kind. That's one of the kind of parts of my statement. Right?
Okay, yeah.
As I go through, this is one of the caveats. There'll be other caveats.
Okay.
But this is one of them.
Yeah.
I should say though that given the techniques we use, there's at least a feeling that we should be able to push it to the non-adaptive setting. It seems more like a question of rolling up our sleeves and doing hard work rather than a fundamental objection. But we don't have that result.
Okay.
So
Yeah.
it is a
I also think that all Alex and Donis things for locality sensitive hashing,
Pardon?
I think the algorithms that Alex presented for locality sensitive hashing were all non-adaptive. I mean, he just went to certain bins,
Right.
based on the hash values and said whatever is in those bins, it's
In
all
fact,
we're
they
going to
have,
care about.
they have a new paper, right? Alex and others have this new paper where they show that if you are allowed to be adaptive, you can kind of push beyond what LSH allows you to
I think that's more adaptive to the data, but anyhow.
Okay, I see. Okay.
Sorry.
Yeah.
Right. Yeah.
But I'm just saying that his lower bounds will capture the kind of stuff that Alex presented.
Right.
Yeah.
Yeah. In fact, we start, because like I said, we start off with LSH. We use you can think of these as LSH type code.
Cool.
But thanks for that. That's a good question. Okay. So what we want to show in this horribly written data grid here is the following. So let me try to parse out what's being said. So what we're saying is that if you do in fact want to build a non-adaptive data structure that has near linear space, that has sort of makes R queries to data structure to solve the problem, then the space you must pay is superlinear in the following form: n to the 1 plus this expression right here. Obviously, if you allow more queries, you should be able to work with less space. That's why the R is in the denominator of the exponent. The more queries I have, the better. But this is the bound you get. And this alpha is basically the min of mu and d over log n, where mu is my structure constant and d over log n comes up for different reasons, which I'll explain. And the way to think about this is to not read the theorem at all, but just to do a pattern matching with what is known for well-being distance functions, like say L1. In particular, this is a result by Panigrahi Talbar Reader from a few years ago. Look at this bound here and compare it. They are identical, and this is not surprising. We use a lot of proof machinery. The main difference is you go from 1 to alpha. The lower bound increases. I'm saying that instead of space n to the 1 plus 1 over CR, it's space n to the 1 plus alpha over CR. Yes?
So just to check that I understood anything. So mu, you gave examples that mu could be almost infinite, right?
Yes, but that's
So,
why
and then the
min
min becomes the d,
Yeah,
and then
the
you have the
proofs are-
horrible dependence on d. Okay.
And there's a reason for that also.
Okay, so basically the asymmetry will kill you completely,
Won't kill you completely.
in the sense that n to the d is horrible.
Essentially what happens, and this is kind of an interesting byproduct, once you get asymmetric enough, your approximate near-neighbor problem starts looking like an exact near-neighbor problem.
That makes a lot of sense.
And then, and this actually matches the known exact near-neighbor problems. I'll talk about this in a few minutes. Pardon me?
He's the second, the other result is a special case. You can derive it from your result.
Well, that would be a very unfair rendition of the result because we use their proof technique. So in a sense, yes, but that's not really fair.
Everyone is a Bregman divergence for with respect to some function.
Sorry, I don't.
Everyone is a Bregman.
L1 is not Bregman. It's not. Yeah. So that's the thing. Bregman divergences have an L1-ish flavor to them. If you sniff at them long enough, they smell L1. I don't know how to explain this other than to say they smell like it. So the natural suggestion was, okay, let's go look at L1. One way of thinking about this is that L2 squared is a Bregman divergence. And I think it would be more reasonable for me to say L2 squared is an L1-ish flavor. I think that's something that people are more willing to accept. So that's yeah. So it's not a generalization to result in that sense because they're doing this for L1. So the important thing here is the idea of getting this structure constant to the lower bound. And I should mention this bound to be pretty big, right? Alpha is mu basically, which is it a constant? Well, yes, except that it can get pretty big. And that's the point here, that as your asymmetry gets worse, you need more space, and that's kind of exactly what we want to say. That the asymmetry really controls how much work you need to do to build a data structure for the solution. Yes?
I'm sorry, did you say, what was the uniform Bregman divergence?
Good, very good, thank you. Next slide has all these caveats. There are a number of caveats here, which I've underlined, so I'm going to explain what these caveats are. So, since you're all eagerly waiting for me to go to the next slide, I will go to the next slide. The first caveat is that this does not apply for an arbitrary Bregman divergence. It applies for a Bregman divergence that is decomposable along dimensions. In other words, I can write it in this form. That it's a sum of Bregman divergences along individual dimensions. This actually holds true for all the popular Bregman divergences. Of course, it's not true. I mean, there are Bregman divergences that are not of this kind. You could define them. But this is one of those annoying technical things that you need to do to make the proof work. Otherwise, you'll carry your hair out. But it's frustrating because it doesn't seem like it's fundamentally important. But I have no idea how to reason about these things without it. But it's a limitation of it. So you have to have that because it's just easier to argue about individual dimensions, and you'll see this next slide. It also works beyond Bregman divergences, and that's the point. The way the construction works only requires a divergence and a sum lower bound. We're not actually using the geometry of the Bregman divergence at all. We're just using the fact that it's asymmetric. So if you give me some other distance function which has a lower bound and asymmetry, in fact, you just need 2 points in R to do this. You can build the entire machinery of the lower bound just from that. So in one sense, it's about Bregman because Bregman is a case where this asymmetry shows up naturally. But really, it's about any kind of asymmetric structure, whether it's Bregman. And this is what I was telling when Mikkel was asking. This bound is in some sense, in a sense, again, in a sense is best possible. Because once you get to that level, and if you require linear space with this mu, you need these many queries, and this is a known lower bound for exact linear research by Barkla and Ramani. Again, their result is stronger. It's an adaptive setting. But it tells us that we're going to have to do a lot more work if we want to push our bound to be further. So in some senses, it hits up against other lower bounds that people mentioned. That's what I meant. Good. All right. So there are some simple things you could try, and they kind of sort of would. Not that least you get to do more. So, but let me explain a couple of them first. So the easiest thing you could do is say, well, we know we have a lower bound for L1. Let's make our space look like L1. In other words, let's construct a mapping from an L1 hypercube, which is the vehicle used to show L1 lower bound. You build a thing on the hypercube, and map it to some kind of Bregman cube, whatever that might be, such that you can show this property. The distance here is exactly the distance there. And in fact, you can do this. There's a constant there, and you can build it. So it's essentially an isometric map scale. But you get only the bound that you get before. So it's like a trivial throwaway. You can get exactly the same bound, but you don't get the dependency you want on the structure of space. You're not using the structure of space at any level. But you can get it. So this is actually useful because it gives you immediate lower bounds for other Bregman type problems. But they're not that useful. So that's one thing we do. A smarter thing you can do is to use partial matrix. As I said, this problem that shows up a lot in near neighbor search as a lower bound proof. The partial match problem is defined in this manner. This is one way of defining it. I given a bunch of vectors p on the hand on the cube, the 0, 1 cube, and I have a query vector. And I want to find if the query vector dominates any of the points in the set. So for all the IPIs, that's an equal. This is equivalent to saying that I have a set of vectors p, and I have a vector q, which consists of 0, 1s, and don't care symbols. unbound because you're relying on infinity. Actually, you need something like this, which is a bit. So you can get kind of one little result, but you can't get a smooth result all the time. So these are two things you can do very quickly that give you some help, but we want to really. Okay. And so the overview of the proof is a little complicated. It involves, like I said, this idea of a directed isochromatic equality, but at high level it looks something like this. So for any problem, if you want to give a randomized algorithm lower bound, you need some kind of hard input distribution of data. So you have to produce a hard input distribution. And if you want to show that any deterministic algorithm on the hard input distribution will give you a bad answer, then you smack it with Gauss max lemma and then declare it. So the way these proofs tend to work is the following. And a lot of the LSH proofs work this way. You build this hard input distribution and you perturb it by a limit to give some error because you're doing an approximate error search. And what you say is that this operator, this noise operator, you can think of it as an operator on the function defining your data structure on this space. You're building some magical data structure to solve this problem, and now I perturb the data so my function, which is my hash function, changes. And then you show this function changes a huge amount. Things go all over the place. Okay? And so in order to get an answer, you have to look at many different spots in the table, and you look. This is a horribly, horribly high level view, which the kind of thing that makes sense for about 10 seconds and after thinking about it doesn't make any sense. But that's kind of how these proofs work. Okay? And I'll try to explain each of these blobs in a bit more detail. And I should mention that for the most part we follow the framework developed by this other paper by Carnegie Van Meter, except that we don't. So we sort of follow it. So again, there's a bunch of related work on this. There are deterministic lower bounds, there are exact lower bounds, there are randomized lower bounds, there are randomized lower bounds for polyspace or nonlinear space, and there are lower bounds for LSH. Some of them go through communication complexity, some of them go through this kinds of arguments, and they're just a whole variety. The communication complexities are particularly nice. This is started off with a paper by Peter von Milterson and has been developed ever since. That you can think of the probing of a data structure as a communication. You have the player asking the question in a data structure which is talking. And so by showing the communication complexity lower bound, you give a lower bound on the space needed for the data structure. Otherwise you shouldn't be able to answer this question. It's a very nice set of things. Alright. So now I will start trying to explain how this works. So about 10 minutes more? So what you want to do is build a cube like the cube, a Boolean cube on which you're going to build your input structure. Okay? And we want a cube where distances are measured one way in one value and the other way they measure. So there's a very simple way to do this. Like I said, take 2 points. So the distance from A to B is 1, the distance from B to A is mu. Once I have that, I can build a 2-dimensional cube that has the same property. The distance from here to here, because of the uniform property I rely on, has distance 1 in one direction, but a distance mu in the other direction. 1 this way and mu this way, 1 this way and mu this way, and so on and so forth. And of course I can do this in d-dimension. I can keep doing this. I can just increase the length. Right, so think of it A as a 0, B as a 1. So I can build a cube in which any distance going forward is mu, a factor of mu different from the distance going backwards. Okay, because you go to 1 this way. That's going to be important. And then what we do is we define a notion of perturbation. Again, because we want to talk about approximate distribution. So we perturb asymmetrically so that there's a different chance of going from 1 to 0, and there's a different chance of going from 0 to 1. So you're not just perturbing things uniformly, you're perturbing them in one direction versus the other. And these numbers are going to be different. And this is called a noise operator. You can think of it as saying I'm doing a little, what I'm going to do is I have a function defined over my cube. Now if I perturb the points in this manner, what is the expected value of the function? That's a new function. So you can think of this as an operator on the space of functions over the cube. So just like you have the undirected noise operator, which shows up a lot in these things, this is what's called a directed noise operator. And this operator is what is used in a lot of Boolean function analysis and Fourier methods for Boolean function analysis. So once you have this asymmetric noise operator, you can now say, okay, what properties does it have? It has the appropriate properties we need. In other words, we take a bunch of points that are reasonably far from each other, and then we do this perturbation. Then if you look at the second set of properties, it's what you expect. Namely that if I have a query, its distance to its near neighbor is small, that's epsilon times d. D is the dimension of the space, and epsilon is my parameter. Its distance to any other point, which is not its near neighbor, is very big. It's mu times d. Think of mu as a much bigger number. So think of this as a gap instance. I better get my correct answer, Because if I don't get my correct answer, my approximation guarantee is going to be weak. So if I do, so in other words, if I am able to solve the approximate problem for this input, I'm actually returning the exact thing, just like any kind of hard instance. And all these things hold high. So now I have a hard instance by doing this perturbation. And this takes some work to prove, but it's not too hard to prove. More or less elementary. And then what you want to reason is this harder. What you want to say is the following, that I said I want this function, my hash function, to scatter a lot over the blue, because I want all my points to be dispersed everywhere. One way of trying to capture this is to say, let's look at the norm of this function. A function that's flattened out a lot has a small L2 norm. A function that's very concentrated has a high L2 norm, right? Because it has big peaks. So if I can show that once I take my function, apply a noise operator to it, and get a new function, that the new function has a low L2 norm, and in some way I've shown this function is spreading out the norm. Okay. This is what is called an isoperimetric inequality. If you think of, for example, Cheever's inequality and how you can show that graphs expand, it's a special case of this. And there are many other results that are all special. The Johnson-Levi-Strauss lemma is a special case of this. They're all special case. Turnout bounds are a special case of this. They're all special cases of this basic idea that things spread out. And that's the kind of result which is called a Bonami-Bregman inequality that looks like this. That when you take the function, spread it out, and look at its true norm, it's less than the original norm. And there's some technical details as to why this is not true, but you can get a second strong one. We'll see. And so the idea is that if you can show that when I take my data and perturb it using this directed operator, you can actually do this nice thing, then you will be able to push through a bunch of machinery to show a lower norm here. And there's only one minor difficulty with this, that it's not true. This is a well-known obstacle to proving these. They're not true. In particular, if you have a directed operator and you're pushing all your points to one corner of a cube, think of a bunch of points in a cube and I perturb them only forward. If I have points in the upper right-hand corner of the cube right there and I push them even closer, they're going to get even more cramped, not less cramped. There's no way my L2 norm is going to go down, it's going to go up. Whereas with a symmetric operator, some of them are going to come back, some of them will go forward, and things always spread out. So you actually can't do this. But it turns out for the purpose that we want, it's enough to show that the function is on the other side of the space, so the lower one here. So even if it goes forward, it is kind of expanding out. Okay. It's kind of a lucky state in functions. We don't need it to work over all functions. It's sufficient to work over functions that are supported over. In other words, my hash function only work over. But that's one issue that makes it difficult. This took us a few months to figure out. And once you have that, you basically do a sort of a not quite random walk through the literature on isoperimetric inequalities to get the ones you need. Namely, what you say is that I have this asymmetric operator over a space, and I want to show that it has the right expansion properties. What I do know is that if I have a symmetric operator over a biased distribution space, where the points are chosen non-uniformly, but I do a symmetric perturbation, I do have such an expansion property. So somehow I get my function to the space. I go from an asymmetric operator R to a symmetric operator tau in a biased space, apply an expansion equality and get from there, which is a known result, and then pop it back here. So there's a lot of, again, there's like 3 pages of calculations to get this whole thing to work. But basically you're able to show that in some weak form, this expands in this form. You can show that this is less than equal to that. That the noise operated version of the function is less than equal to the original norm. Which is good. So you get this kind of isomorphic equality you need in order to sense. And what it means is the following. We said that the function expands a lot. What it means is that suppose think of this as being one hash bucket. All the points here are hashed in one region. Now think of this all these points here. Okay? So if you look at any smaller region of the hypercube, because of this expansion property, only a small portion of the ball around the point goes to any particular region. This is a small region of hypercube. I'm saying what points get sent there. Very few points get sent there. And more generally, if I partition the ball around the point in various pieces, they go all over the place. So think of it this way. I have a point here. I'm looking for its nearest neighbor. It could be one of these points here, but they go to different locations, far away from each other. So I have to do a lot of work to find this. It's the high level. Again, I don't want to get into technical details. It gets long and boring. But you can maybe get it for that. But that's the high level. And the final thing we have to do is this very cool trick, which if you remember nothing else in this talk, I would like you show that there's a lower bound on a data structure for solving some problem. Forget about everything I told you. Just think of some data structure, have some space S, you can do n queries, and you want to show that it has some lower bound in space. So fix some input points that you want to reconstruct. Input point that you want to reconstruct that is near to you. And sample a fraction of the cells of the structure you have. Okay? So think of this, I have a query, it goes into my structure, it looks at the cells and answers based on that. I'm only going to sample a subset of these cells. So if my query hits something that's not my sample, my query goes up. Like I can't do anything. Okay, so only a few of my queries will survive this process. So only some of the queries will work. If you can show that even one of these queries work, then you've reconstructed this point using a very small sample of the input. And then there's this wonderful inequality from information theory called Funnels inequality that says that if you can, then the mutual information of this channel communicating that point to is reasonably large. And the size of the sample must be reasonably large. Therefore, the size of the data structure must be reasonably large. You can think of Funnels inequality as a generalization of the idea that that if you have 2 to the n things, you need at least n bits. We all know that. Funnels inequality is that on steroids. And it's very important. So you need this tool, and this again has been used by many people to get strong lower bounds for certain data structure problems. Casper Larson has a very nice exposition of this technique in some of his recent papers. And once you do that, basically, roughly speaking, the hypercontractility that I showed you, this expansion property, implies that all the queries that you want that hopefully could work are sent to different cells. So even if I only sampled a few of them, some of them are going to work. Or at least one of them is going to work with a reasonable probability. Make the probability balance. Okay, so I'll stop here now. We're getting close again. And there are a couple of different questions one can ask you, depending on what you're interested in. If you don't care about vector divergence, you do care about directed isoprem, then, if there is some hint, and Amir and I have been talking about this the last few days, that it's not just that you can use partial match to prove a lower bound for our problem, in that you could use directed isoprem to provide a different proof of the lower bound for partial match itself. And that would be kind of interesting, that this idea of directed isoprem gives you a bit more power in your lower bound structure to prove lower bounds for some of these problems. So there's this sort of fairly strong result by the hypertrust one showing on lower bound, and I'm hoping to see, there may be a way to either reproduce that result or maybe even strengthen it a little bit. Again, I don't want to say I'm going to start saying wrong things very morning, but there's some hope. And again, of course, we'd like to make our result adaptive. This is kind of an annoying thing that we'd like to fix. And more interestingly, I think this hypercontractility idea, this idea of expansion, shows up not just in data structures. It shows up improving hardness of approximations, most notably. It shows up improving the hardness of Boolean function size, things like understanding Boolean functions, doing machine learning. And does it make sense to